Good day and welcome to my office. I'm Dr. T. So let's take a look at bonding. Atoms need to stick together, the classic everyone needs someone. Well, atoms tend to stick together in one of basically three different ways. This is not an exclusive three. There are some kind of hybrid approaches, and there is new work in discovering some alternative approaches that atoms can interact with each other that aren't really covered in what I'm about to describe. But with that said, there are three major ways of bonding. What we call ionic bonds, which should be ionic bonds. I'll explain the quotation marks here in a minute. Covalent bonds and metallic bonds. So let's start out with the metallic bonds. As chemists, we actually deal with these the least. Metallurgy is really its own thing, and the metallurgists deal mostly with the metals. We chemists, a little bit, but not much, to be honest. Okay, so let's look at some metals. With metals, you're going to have a bunch of atoms, and we usually think of them as a bunch of nucleuses. They'll, of course, have their core electrons and some of their valence electrons. But metals tend to be very low electronegativity. They tend to have relatively low first ionization energies as well. And they're not going to ionize truly, but they will be sharing their electrons with the group. They create what's known as an electron sea. Think almost like an electron commune. This actually gives most of metals' properties to metals. The electron sea allows them to conduct electricity really well, actually shockingly well, because, hey, you get a bunch of electrons. They can flow. It also makes them relatively malleable because the nucleuses can slide past each other. They're not going to have any kind of alternating charge or things that are going to break them apart. Now, you still get some crystallization in here, and you can get good old stress factors, but you are able to move the nucleuses around, at least somewhat, within your metal. Now, I mentioned a little bit of crystallization. You do generally get some kind of 3D pattern of your nucleuses. This 3D pattern is known as a lattice, and this is going to be a relatively important thing for many of the compounds that we're going to be dealing with, especially those that are going to involve metals, whether it be a pure metal in a metallic bond or a metal and a non-metal in what we refer to as ionic bonding, which will be up next. Speaking of which, let's talk about ionic bonding. Ionic bonds are going to, of course, occur between ions. But remember how I put the whole air quotes on those? These guys really aren't bonds. Bonds imply the sharing of electrons. And while some ionic compounds do share electrons to some degree, the classic ionic bond isn't really a sharing relationship. It's more like a theft. The idea here is that you have ions. Cations, which have at least one less electron, so they have a positive charge. They might have more than one less electron. And anions, which have at least one, if not more, extra electrons. Now, it's a bit of a misconception to get the idea that the anions acquired their electrons specifically from the cations. That could be the case, but odds are the anions have been anions for a very long time, and those cations have been cations for a long time, and they simply happen to have arranged themselves in this particular crystal structure, the arrangement known as a lattice, relatively recently. Now, with ionic bonds, and once again, bonds, the lattice actually plays a huge role here. In this case, every ion is surrounded by many other ions, all, generally speaking, of the opposite charge. So you might have one anion surrounded by, say, 4, 6, 8 cations, and vice versa. This surrounding with charge leads ionic lattices to be incredibly strong. Far tougher than metals, although because they do tend to alternate positive and negative, and while opposites attract and likes do repel, so if you were to shift them over just a little bit, all of a sudden you would have cation on cation, and boom, they pop apart. So ionic compounds tend to be very hard, but also a tad bit on the brittle side, because once you start to deform them even a little bit, they will break. The third type of bond is the covalent bond. Now, unlike ionic compounds, these don't have a effectively electron-stealing relationship. You don't have cations and anions. And also, unlike metallic bonds, you don't have an electron sea. Instead, we are sharing electrons, like the metallics, but it's a discrete relationship between two atoms. Two atoms will presumably each bring an electron to the party and form a bond. This is not always the case, but it's often enough that it's a good way of thinking about it. Now, an atom may have several bonds with different atoms, but those bonds aren't shared between all of the atoms. They're individual discrete relationship. This kind of goes back to what I like to refer to as the bad dating advice model of chemistry. This is like an individual having several friends. Those friends don't know each other, but they all know the one individual. And in this case, that one individual happens to be an atom. Now, with covalent compounds, they can come in actually two forms. They can still have a lattice like the other ones. These are called covalent network solids. Examples would be things like graphite and diamond, or even glasses, which are what we call amorphous. They don't really have a pattern. It's hard to say it's a lattice, but they do have a network. Bunches of atoms all sharing, kind of like a great big network of friends. Not like a pool of people who all know each other, but kind of like a 6 Degrees of Kevin Bacon kind of thing. Now, covalent compounds can also come in molecules. Molecules are discrete clumps of atoms. They might interact with other atoms or other molecules, but they're not bonded to them. So if you think of, say, a water molecule, that is one oxygen and two hydrogens. The oxygen has a bond or a relationship sharing electrons with each of the two hydrogens. The two hydrogens don't share electrons with each other directly. Also, that's it. There is no lattice. It's its own discrete clump. And that does give molecules a rather interesting set of properties and does lead to other interactions, because now we can talk about interactions of molecules. Discrete, difficult to break apart clumps interacting with, shall we say, less stringent interactions. Think families interacting with each other. We're friends, but family's family. Now, no talk of lattice would be complete without talking about polymorphs. Polymorphs are the same compound, but with a different lattice structure. This is not something you usually see in ionic compounds, but with molecules, when they start forming lattices, once again, kind of what we refer to as intermolecular forces holding them together, or with molecular solids, you can get different lattices for the same compound. These lattice structures will give somewhat different properties. Actually pretty obvious that they would. And once again, we call these guys polymorphs. Not something we're going to dive very deep into, but is something to be aware that these things do exist, especially with the molecular solids, things that are made up of individual molecules. The network, or covalent network solids, not really such a big deal in ionics. Yeah, they don't really do this. But the molecular solids, they've got a lattice, and they can have different lattices depending on what's going on. But with that said, have a wonderful day.